Today we're doing some more Calculus 2 practice problems focusing on fluid force. So fluid force is very similar to work, what we did in the last video. Fluid force is just pressure times area, where pressure is given by the weight of a plate times its depth, and where area is the area of a plate. This plate is submerged in a fluid, right? So we also need to know the weight density of water. If we're in the metric system, it's 9,800 newtons per cubic meter. Customary system, 62.4 pounds per cubic foot. The units on force are either pounds in the metric system or newtons or pounds in the customary system and newtons in the metric system, right? So let's look at this example. What is the fluid force on this plate, assuming that we're submerged in water, right? Well, the fluid force, first we need to find the pressure. The pressure is just the weight of this plate, or the weight density of water, times the depth that it's at. And it says that it is at a depth of 5, right? Finally, or actually we are in the metric system because of these units right here, 4 meter and the 3 meter. So we're at a weight of 9,800 instead of 62.4. And the fluid force is just pressure times area, right? So what is the area of this plate? Well, if it's 3 meters by 4 meters wide, just get an area of 12. So you can crank out this number. That would be the fluid force on this plate. That is 12 square meters and being submerged 5, right? And the units on that will be, since we are in the metric system, newtons. Okay, but we didn't have to do any integration or anything because this is almost like a slice itself. If we have a vertical plate, however, things get a little different. Let's look at the fluid force on the vertical side of this tank. This tank can be represented by y equals x squared, which is given. So what we're going to do is we're going to find the fluid force on one of these little slices, right? And we're going to add it to this one and this one and this one, all while making them infinitely skinny, right? So we're fairly used to this process now, and that's how it becomes integration. So let's see, we're going to have to throw this onto an axis, right? Let's put this on a y-x axis, xy axis. Here's our function. It would only be 2 there. This is still y equals x squared. Now, what I'm going to do is I'm going to find the fluid pressure on just half, right? I just want to find the fluid pressure on this half, and then I'm going to double it because it's symmetric. So let's find the fluid pressure. Let's find the fluid force, and we start with pressure. So pressure is the weight, which is, in this case, we are in the customary system, so the weight of water is 62.4 pounds per cubic foot, and we're multiplying by the depth that any of these slices are at. So this just depends on the way that you set up your axes, right? But what is the depth of this slice right here? Well, we should be fairly used to this process too. This slice is at a height of y, right? And its depth is given by this. But we also know this, right? This is 4. So we can see that this depth right here is just given by the difference between whatever y value it's at and that total height of 4. So the depth is just going to be 4 minus y. And we can check this. When these slices of water are all the way here at the top, right? What is their depth? Well, they're at the top, so they have a depth of 0. This is kind of like the water level, 4. So you can see when you plug in 4 into our depth function, we do get 0 because we're at the top of the tank. What about if we're here at the bottom at y equals 0? What is the depth, meaning how far are we from the top of this tank? Well, plug in 0 into this function. You're going to get 4 minus 0, which is 4. That is because we are 4 feet from the top of the tank. So this is a correct depth function, right? Now, we need fluid force. Fluid force is going to be, and let's call this delta fluid force. This is just the fluid force of one of these slices, right? So this would be the fluid force. We're going to do 62.4 times 4 minus y. How do we get from pressure to fluid force? We multiply by area. So what is the area of this slice right here? Well, you can see that these slices in the tank are just rectangles, right? So those are going to have an area. They have a width of delta y, right? We're familiar with doing this. So their area would be delta y times their length. But what is the length? The length is changing depending on the y value. For example, here when we're at y equals 0, they really have a width of 0. But up here at y equals 4, they have a width of 4. So how can we relate the width of this slice to the function? Well, we said that this function is y equals x squared. If we call that x equal the square root of y, and we're choosing the positive square root because we're at positive x values, right? Well, remember, the slice also comes over to here. So we can just double the result. We can double the width of just this, and then that'll account for the entire tank. So the width of just, this slice right here is the displacement between the function and 0. For example, right here where the function meets 0, there's no displacement, hence no width. So we're going to call this the square root of y minus 0. Now let's test this. And I also want to double it to account for the other side of the tank. 2 square roots of y would be the width. This right here would be the width of any given slice, right? So up here at y equals 4, right? This part corresponds to up here at y equals 4. Up there at y equals 4, do we have a width of 4? Well, let's plug it in. Plug in 4 into this function. You're going to get 2 square roots of 4, which is indeed 4, right? So far it's correct. Let's also check the bottom of the tank. At the bottom of the tank, when y is 0, we should have a width of 0. We can see that there's no width down here for any slice at the bottom of the tank. When we plug in 0 into our width function, we get 2 square roots of 0. So yes, it seems like a good function to me. So let's look at, that is our delta fluid force. That is a fluid force of one arbitrary slice, right? So how do we find the total fluid force? We can just integrate that delta fluid force. So we're going to integrate that 62.4 and that 4 minus y and that 2 square roots of y. It becomes a dy now. Where are these slices moving from and to? Well, they're starting all the way here at 0, and they're moving all the way up to here at 4. So we're just integrating from 0 to 4, right? Now, let's see if we can pull the 62.4 and the 2 out of the integral. And so double 62.4, you're going to get 124.8. Then we're integrating from 0 to 4. Let's distribute this square root of y into there and there. We're going to get 4y to the 1/2 minus y to the 3/2. So this is a very doable integral, right? And if you're allowed to use your integral capable calculator on the test, you could just stop right here and plug it all in, right? But we'll go a bit further. 124.8, integrate 4y to the 1/2. So you add 1 to the exponent, divide by that new number. We still have that 4. Add 1 to this, and divide by that new number. And then finally evaluate at 4 and 0. So you can plug all of this into your calculator. I'm going to skip that part and just say that this answer is equal to 1064.96. What are the units on it? Pounds, because we are in the customary system, right? So that is how we do fluid force. Let's look at this. What happens if the tank is now submerged underwater? How does that? Well, this would affect the depth, right? The depth is no longer from the top of the tank, it's from the top of the water. For example, even though the slice right here is at the top of the tank, it's still 2 meters deep, right? 2 meters underwater. So let's find the fluid force on this vertical plate submerged in water. The plate is a square, it's 2 meters underwater, and it has dimensions or side lengths of 2. So once again, we're going to find the fluid force on just this thin slice, right? Remember the example we looked at. We really just found the fluid force. Since this is a horizontal slice, finding the fluid force requires no integration. But when we're looking at a vertical plate, we're going to find the fluid force on one of these slices and then integrate from the bottom of the tank to the top of the tank, right? So we need to find the delta fluid force, or the fluid force of just one slice, and we first do that by finding the pressure of this slice. It is the weight of the water. Since we're in the metric system, that's 9,800 newtons per cubic meter. Also times the depth. So what is the given depth of any of these slices? Well, we can put this on an axis, right? If we put this on a XY axis just like this, we can see that since this is 2 meters and this is 2 meters, this is like a y value of 4. And we already know from the last problem that the given depth of any slice is the displacement between that top function, y equals 4, and the given y value that this slice is at, right? So for example, if they are at a height of 2, they are at a depth of 2, right? And if any of these slices are at the bottom of the tank, they are at a depth of 4, right? So we know that this depth function is correct. So the pressure of just this arbitrary slice is 9,800 times 4 minus y. And the delta fluid force would be the pressure times an area of one slice. So let's see, it's going to be the pressure, which is this, times the area of one slice. And you can see all these slices have the same area, actually, just a width of delta y and a length of 2. So it's going to be 2 delta y. Finally, we're going to integrate to find the fluid force. The fluid force is the integral 9,800 times 2 times 4 minus y. dy, the delta y turns to a dy. And then we have, where are we integrating from and to? Well, the slices start at the bottom and move to the top of this square tank. So we're integrating from 0 to 2. So the fluid force, we can pull out the 2 and the 9,800. Right, or actually, yeah, let's pull out the 2 and 9,800. That's going to be a 19,600. And then we're left with just integrating that 4 minus y dy. So that'll become a 4y minus 1/2 y squared. We're evaluating that at 2 and 0. So the fluid force is 19,600 times 8. And let's see, when we plug in 2 into this function right here, we're going to get 2 squared divided by 2. So just 2. So 19,000 times 6 is equal to 117,600. Since we're in the metric system, units on fluid force is just newtons. So this one was not too bad because of that width function was not variable. Okay, but let's look at one more. Obviously the width function is variable. any slices at the top of this triangular tank have no width, but any slices at the bottom have a width of 6, right? So let's find the fluid force on one of these slices, the delta fluid force. We know that that's pressure times area. So what is the pressure of this slice? Well, we are in the metric system, so it's going to be the weight density of water times the depth. What is the depth? It's the same kind of strategy. We got to put this on an axis, right? Something like that. We can see that since this triangular tank is 9 meters tall and it's all 3 feet underwater, that this sea level really happens at y equals 12, right, where the bottom of the tank is at y equals 0. You could set your y equals 0 to be at the ground or sea level or at the top of the tank. It doesn't matter. It's going to change your depth function and your area function, and may or may not be easier to integrate. But I'm going to choose the bottom of the tank as my ground level, or y equals 0, because it'll be easier to find what this function is. So let's see, what is the depth function? Well, the depth function is the distance from 12 to the y value of the slice. Once again, it's going to be 12 minus y. The fluid force of this slice, right, the fluid force of this slice is going to be that pressure times the area of that slice. So what is the area? It's a rectangle with some width, delta y. What is its length? Well, like I said, at the bottom it's 6, at the top of the tank it is 0, so how can we relate? Well, let's find the equation of this line right here. It's a line, right? So it's y equals mx plus b. We know what b is, the y-intercept, based on the way that we set up this plane. The y-intercept is 9. And we can find m because we know that it moves down 9 and over 6 to this next point, right? So the rise over run, that's what m is, the rise over the run. The rise is -9, and it runs 6. -9 over 6 is the same thing as -3 over 2, right? So the equation of this line is y equals -3 halves x plus 9. Okay, but we want to solve it for x because we want this area function right here to be a function of y, since we're going to be integrating with respect to y. So we've done that a lot of times by now. So let's solve it for x. We get y minus 9, and flip the fraction. This is what is equal to x. So this x is like the width of one of these slices, right? So now we can also distribute this -2/3 in. We're going to get the width function, I'll just write it in, is a -2/3 y. 2/3 times 9 is plus or positive 6, right? So if we want to find the fluid force, we'll just integrate. Where are the slices moving from and to? They start at the bottom of the tank at y equals 0, and they end at the top of the tank at y equals 9. So we're going from 0 to 9. We can pull this weight density out. That leaves us with a 12 minus y and a -2/3 y plus 6. Okay. So we can, and the delta y turns to a dy. So we could distribute. First, we have a 12 times a -2/3. That's just a -8. 24 divided by 3. A -8y. Outer, we have a 12 times a 6. That makes a 72. Inner, we have a -y times a -2/3 y. That's going to give us a positive 2/3 y cubed. And finally, last, we have a -y times 6 to get a negative 6y. So the fluid force is 9,800, integral 0 to 9. We have a negative 8y and a negative 6y. That makes a negative 14y. We still have that 2/3 y squared, not y cubed. Right, then we have that 72. So the fluid force is 9,800. Let's do the integration. We have a negative, add 1 to the exponent, divided by that new number. And we're going to evaluate all of that at 9 and 0. So I'm not going to do that one in the video. You can just plug it into your calculator. You get a big number though, 2,381,400 newtons. Big fluid force because it is a big plate submerged deep underwater. So that is how we do these fluid force problems. We looked at a triangle, a square, and a parabola-shaped tank, right? So that's how we do fluid force.